Hello and welcome again. The IB Chemistry exam for May 2021. It's happening on Friday, which is just a matter of under 72 hours from now. Here in India, no students will be taking the exam, but this video is intended to go over topic 11.3 spectroscopy, and it's made for all of you students out there who will be taking the exam on Friday. So let's move in and take a closer look. So here in this past paper question, we begin with the structural formula of urea shown here. C double bond O with two identical NH2 groups attached to this carbon atom. And this particular question examines all three aspects of spectroscopy that are related to section 11.3, the SL part or the core part of the IB chemistry guide. And in this first part of the question, the structure of urea has to be related to its mass spectral data. And here you can see that mass spectral data is provided, and the student has to identify why you have a peak at 60 and then another peak at 44. Now usually the students will go into the data booklet and simply read off what that peak is from the data provided there. But sometimes students are expected to figure out on their own what causes the peak without extracting it from the data booklet. And that could present some issues unless you get a few tips. So one thing you must always know is that the only peaks you could be expected to be responsible for are the ones in the booklet, but we've got a few exceptions. The ones in the booklet are listed there for you, but you should always be aware that for any molecule that you put into the mass spectrometer, you are going to get one peak that corresponds to its full structural formula as it forms a charged species. So think of C double bond O, NH2, NH2 with a positive charge, and that being inside of the mass spectrometer. The relative intensity of the peak associated with that entity is going to be 12 for carbon, 16 for oxygen, 28 for the two nitrogens. All of that comes to 56 plus 4 for the 4 hydrogens, and that gives you your peak of 60. The peak of 44 is also not presented in the data booklet. So then you've got to look at the structure of the molecule and reflect on how it could be possible for this molecule to fragment, and what fragment could end up being 44. Well, if you remove 14 from nitrogen and plus 1 15 and plus 1 16, this entire NH2 is removed here, then the remainder of the molecule, that entity, would have a relative intensity corresponding to 44. Here in this question, you are provided with the readout of the infrared spectrum of urea, but you're asked to identify why do you have an absorption at 3450 and why do you have an absorption at 1700, these two wave numbers. Now, these absorptions are happening here, as you can see. This is transmittance and this is absorbance, and here you have another huge absorbance. All of this is good for helping you to understand the nature of an infrared spectral readout, but none of this is actually required to score the marks in the examination. All you need is to take this bit of data, and have a look at the molecule, and you might think intuitively that it's got to do with this functional group and it's got to do with the NH2 group, and that of course is totally correct. But when you go into the data booklet, it will be confirmed. And here in the data booklet, you would see that the C double bond O, which corresponds to aldehydes, ketones, carboxylic acids, gives this wave number. and it's very strong, as we saw in the infrared spectral data. And similarly for the NH structure, this NH2 structure that you get in primary amines, which is what you have there in the structure of urea, this NH, which is a part of NH2, that gives this readout 3300 to 3500. And those two structures are the ones that you should identify as being responsible for those two absorbances in the infrared spectrum. And the final component of this question dealing with the structure of urea has to do with the hydrogen-1 nuclear magnetic resonance spectrum. The H1nmr spectrum seeks to identify hydrogen atoms that exist in unique chemical environments. What does that mean with respect to this molecule? Well, you have a nitrogen that's attached to a carbon that's attached to a double bond O. That nitrogen contains two hydrogens attached to it. And then the other nitrogen here on the other side is very much a mirror image of this one. So what you have are 1, 2, 3, 4 hydrogens, and all of them are in chemically identical environments. So therefore, the H1nmr spectrum is going to identify all 4 of them as being in the same chemical environment, and its readout is going to produce a single peak that corresponds to 4 hydrogens. So that would be your answer for this question. It will be one single peak that corresponds to 4 hydrogens, and that is what you would see on the H1nmr spectrum. So in this particular case, there is no need to make reference to table 27, which provides all of this NMR spectral data. To give you some more practice with NMR spectroscopy, I have included here another question, this one from a more recent examination. And here, students were first required to write down the structure of diethyl ether, which is given here. But I've also given you the condensed formula for diethyl ether here to remind you of how to write a condensed formula. And note that this is a carbon and it's attached to 2 hydrogens. That's understood. Once you have a structure like this, bending like that, it's a carbon that's fully saturated. If it were unsaturated, you would have had a double bond going across like this, and here a CH3 and here a CH3. So this is your structure of diethyl ether. And students were asked to identify the number of peaks that you would get and the ratio of those 2 peaks. The answer to that question is that you would have 6 hydrogens here in one chemical environment, and these 2 and these 2, another 4 hydrogens in another chemical environment. So the NMR spectrum would have a ratio of 6:4 or 3:2 for these hydrogens. And 6 hydrogens in one chemical environment, 4 in another chemical environment. Now, if you need some more practice with these kinds of questions, you can click on these cards above and you would be able to access 2 multiple choice questions where I explain applications of hydrogen-1 NMR spectroscopy.